So I will summarize the logic of OLS and what is a regression analysis, and I will emphasize some terminology that might help to you while writing your proposals. In this present, I believe most of you have already familiar with the concepts and OLS, and maybe you use more advanced methodologies, but it's always good to be reminded with this properties of we might forget those basics, and I believe it will help you to understand the difference in differences design and regression discontinuity too. You can interrupt me whenever you want. First, I will go over the slides and some basics of regression and OLS assumptions. And in the second part of my presentation, I will show you how OLS in R, using R. So in that part, you might need to open your computers and R to code with me. So let's start with the basics. So a regression is defined as the statistical models to explore the relationship between a response variable and some explanatory variable, between a dependent and independent variables. And it's about the expected value of y conditional on a single x in the bivariate case, or multiple x's if it's a multivariate regression. This is a terminology note here, is that we explain y in terms of x in regression analysis, or we study how y varies with the change x. If we give an example, it might be something like studying how AKP vote share varies with changes in the level of development regions, for example. So I will start, and mostly will continue with bivariate linear regression model. It is also known as simple regression model or two-variable regression model, but it is more or less the same with the multivariate version. I will refer to that whenever it is necessary. So our simple regression model is written as you can see here. So y equals 0 plus beta 1 multiplied by x, which is our independent variable, plus some error term. Here, again, a terminology note is that we always regress variable, which is y, on the independent variable, which is x. So we regress y on x, or we run the regression of y on x always. Help you with the terminology again. There are several names that we gave to those y's, x's, betas, or errors. So y is our dependent variable or explained variable, predicted variable, or regressant. All of them are same. And x is the independent variable, explanatory variable, control variable, predictor variable, regressor, or covariate. And the epsilon here is the error term, or we can call it disturbance, or the random component in our model. This captures the factors that can affect y, that can affect our dependent variable, other than our independent variable. We will be talking about the error term in more detail. So yes, and beta 0 is the called intercept parameter or constant, which captures the average value of y when x is equal to 0. And beta 1 is the slope parameter or slope coefficient for our independent variable. There might be multiple betas like beta 1, beta 2, beta 3, dependent on your number of independent variables. This is why I wrote this is the slope coefficient for x1 here. So in OLS, we have basic assumptions. In order to apply OLS, we have to assume that the relationship between x and y is linear. So given the values of these explanatory variables, like x's or just a single x, you may predict the values of the dependent variable, the y. And we assume that the change in the error is 0. And when we assume that we see that the relationship between y and x is linear. So a change in x is related to the change in y. This means that under ceteris paribus, which is holding all the other things fixed, x has a linear effect on y. So what does it mean? The linearity between x and y means that a 1 unit change in the x in the independent variable has the same effect on y regardless of its initial value. And also a 1 unit increase or decrease in x will change the expected value of y by the amount of beta 1, which is the slope. The direction of this change will be determined by the sign of the beta coefficient. So these might sound somehow abstract right now, but I will show some graphs to you, then it will be better. Just bear with me right now. So how do we get this beta 0 and beta 1? We estimate them by using our data. And once we estimate them, the estimates of these parameters are shown by heads, these signs that you see here. So beta 0 head and beta 1 head are the estimates of beta 0 and beta 1 that we estimated using our data in hand. And once we obtain those betas, those coefficients, and draw our regression line. So I will show the regression line and betas here, but let me just cover this part first. So as you can see, patient changed. I added heads here because these are the predicted values now that the estimates that we estimate using the OLS. So y hat here, so this I will not pronounce them one by one, but this I refers to a single observation here. So this y hat is the value we predict for y when x equals to xi for the given intercept and slope. And there is a fitted value for each observation in the sample. So there is a prediction for each observation in the sample. Those fitted values, those predictions is on the OLS regression line. And we use these least squares to estimate the line's intercept and slope. And how do we do that? We basically try to minimize the sum of squared residual, sum of squared vertical distances, deviations from the observed points to the line. So we try to keep it as small as it can be. This is why it is called the least, because the OLS minimize the sum of squared residuals, which I will again in a graph. So let's take a look at this graph. So those dark blue points are our actual observations in our data. So this is what we observe while x is that specific value, the y gets this value. So this is in the data. And this red line, our regression line, or the fitted line, as it's called. And this is a prediction for y given this specific x. And the difference between what we observe, what we predict, is the random error for this xi value. When x equals to 0, our fitted line, our regression line, fitted line and y-axis has this point which is called intercept. So when x is equal to 0, value beta 0 gets is called intercept, which is here. And we can calculate beta 1 by dividing by finding this. So it is the slope, as you can see. Y divided by x is the beta 1. To show a more, I don't know, understandable example. So as you can see, the grumpiness score, and this is the hours of sleep that I can get. And this is these purple points are the observations in our day. And the intercept is that if this is intercept, this is fitted line, etc. And as you can see, there is this difference between observation and with the fitted line, which is the errors. And the fitted line is in a place that ensures the minimization of this sum of errors. And here the slope has a positive sign, so which means that as x increases, y also increases. But here the slope is negative. There's this negative relationship between that. So as hours of sleep that I can get increase, the grumpiness score will decrease. Yes. So as we already talked about, the least squares should be the aim of the least square is the minimizing the sum of squares. Maybe we should define those. And there are 3 sum of squares, and they generally very hard to keep in mind because their names even are very like similar to each other. And let's start by sum of squares total. So this is the differences between the observed dependent variables and the overall means. So this is the mean y. So this is the mean of the dependent variable, and this is the observed dependent variables. When we get the differences of those and the square of it and sum all of them, we get the sum of squares total. And this gives us the total variability in the data set, such it varies. And sum of squares error is the difference between the observed and the predicted values. So this is the predicted value of y, this is the observed value of y. When we of those, we get the sum of squares errors. And this is in regression analysis, we try to minimize the sum of squares error. And the smaller the error, the better the regression power. And lastly, we have sum of squares regression, which is the sum of the differences between the predicted value and the mean of the dependent variable. And it describes how the line fits the data, how well we predict the result, the y. And we can also calculate the sum of squares total by summing up the sum of squares and sum of squares regression. Now it might sound a bit confusing, but with this graph, I believe this will be much better. So as you can see, sum of squares error is the difference between the actual observation and what we predict. So this is SSE. And sum of squares regression is the difference between the prediction and the mean value of our dependent variable. And when we sum those, we get the SST. As you can see in this, I hope it's now much clear. And let's take a look at our estimator, OLS estimator. Here we will be talking about the assumption of OLS to make the coefficients unbiased. In OLS, we assume that the mean of the error is always zero. So residuals always sum to zero. And our independent variable and errors are not correlated. So the first one is can be written as this. Second assumption can be written as follows, this one. And these are mostly called first order conditions in OLS. And by following that, we can calculate residual for the ith observation. So if you do the math, you will get this formula. So this shows that. And this is, again, get us to the our first two assumptions in terms of y, where the first condition is that the expected mean of the disturbances of the residuals, and the second is that the covariance of x1 or all x's in the multivariate case and the disturbances are both equal to 0. We consider the sample size, let's call it n, the estimates of the population parameters, so the beta zeros and beta ones can be stated as follows. This is how we minimize the coefficients, how coefficients minimize the sum of square residuals. And in order to do that, we must solve the first order condition. And this is actually is the same, like doing this is the same as taking the partial derivatives of the sum of this with respect to the unknowns. And it is another way of driving the OLS estimator. This is just kind of math here. Yes, so this shows that any independent variable is uncorrelated with the error term. And we said that the sum of residuals should be equal to 0. And if the sum is 0, then the mean of the residuals must also be 0, because the sum is divided by n gives us the mean. And again here, another property is regression line passes through the means of observed y and x, and it implies that the intersection of means, this y, the mean y minus mean x and beta hats equals 0, implies that the intersection of the means with the regression line. And this is again because we equation by minimizing the sum of spared residuals. So to summarize all the assumptions of OLS, we may start with the linearity assumption, and those assumptions make sure that our coefficients are unbiased. So the first is linear in parameters. So x is a function of x is a linear function of y. So there is a linear relationship between our independent and dependent variable. The second assumption is that there's no perfect collinearity, which means that no exact linear relationships among the independent variables. So our independent variables, if there is more than one axis, they all should be uncorrelated with each other. And that sample variation in the explanatory variable, which means that none of the independent variables is constant. As in the name, variables should vary. For example, if you want to take a look at the effect of the regime type on, I don't know, foreign direct investment, FDI, if you only include democracies, there won't be any variation. This would not be a selection of a good cases. So there should be both democracies and autocracies, that so that the regime type variable vary across different types. And the third assumption is the zero conditional mean. It is also called exogeneity assumption. And this is very important, and we will be talking more about this. So the assumption says that the error has an expected value of 0 given any value of the explanatory variable. So if we violate zero conditional mean assumption, our coefficients will be biased, and we might end up with omitted variable bias or endogeneity, and these are the very important problems that we face if we encounter with this, and we will be talking about those. And the fourth one is about homoscedasticity and serial correlation. So homoscedasticity means that the error term has a constant variance across all values of the independent variables. This might seem somehow abstract, so I will maybe after also stating normality of errors. So the last assumption is about the normality of errors, and this means that residuals are independent and identically distributed. So the error term is assumed to follow a normal distribution. The definition of homoscedasticity and normality of errors might seem confusing and similar to you, but normality of errors is concerned with the distributional assumption of the errors, but homoscedasticity is focuses on the variance, so constant variance. In here, you see homoscedastic normal errors. So as you can see, they are the errors are normal here. They follow a normal distribution, and they more or less has the same constant variance. Um, Also, let me show you homoscedasticity here. So homoscedasticity has this constant variance across all variables. But if the error variance depends on the predictor, depends on the independent variable, we say that it is heteroscedastic and it follows such distribution. As you can see, here is different from there. So that there is no constant variance in here. And in this case, we use heteroscedasticity robust standard errors. And I've shown the serial correlation part. So the error terms should not exhibit serial correlation, meaning that they should also be independent of each other. Yes, so after obtaining the estimates of the population parameters, after estimating our model, we should assess how well the model fits the data. And for this, some measures to assess the quality of the regression fit. And this process is known as the goodness of a test, and these are the goodness of fit measures. First one is residual standard error, which is which estimates the standard deviation of the residuals in the average distance between observed and predicted values. And by calculating the ratio of residual standard error to the average value of the dependent variable, we can obtain a measure of prediction error. And if our prediction error is low, this indicates the better fit to data. So the lower is the better here. Another and most commonly used goodness of fit measure is R squared, and it represents the proportion of variance in the dependent variable, which is explained by the independent variables. And this is calculated by dividing the SSE, sum of squared errors, divided by sum of squared totals. So since SSE can never be higher than SSE, it ranges from 0 to 1, and higher values indicate a better fit for R squared. While interpreting R squared, we generally multiply it by 100. For example, if we have a R squared value of 0.8, we say that our model explains 80% of the variation in the data. So, but it is not always a good measure of goodness of the fit, and we should be careful while interpreting the R squared, and we should be taking into account our specific properties of our data. And R squared generally tends to increase when we added more independent variables. When we added controls, it increases. So we adjusted R squared in this case because it penalizes R squared for each additional number of controls, each additional number of predictors. And lastly, we can use F-statistic, which tests the overall significance of our regression model. And a significant F statistics suggests that our model and our data fits well. Before omitted variable bias, maybe I should focus on the violation of exogeneity. We mentioned the zero here. We mentioned zero conditional mean assumption, which is the same as the exogeneity assumption. And this says that the mean of the error term should not depend on the predictor, should not depend on the dependent or independent variables included in the model, and the unobserved determinants of the outcome variable, since they are included in the error term, they should be uncorrelated with all the observed predictors. They are not, we said that the exogeneity assumption is violated. And in observational studies, it may be violated because it's very hard to include all the related controls in our model. So how do we do that? In experimental studies, we make sure that control groups have the same quality, same let's say characteristics other than the variables that we. But in observational studies, it's a bit problematic. In order to ensure that we do not violate the exogeneity assumption, we compare the treated units with the similar control units, and we can solve this problem by measuring the confounders and including them as additional predictors. So how do we do that? We generally look at the previous literature and we come up with some control variables and add them in our model to avoid this violation of exogeneity. And also we might refer to some other methodologies to make sure that we do not violate this assumption. So if we violate exogeneity, we might end up with omitted variable bias, for example. So this means that omitted variable bias means that the problem of excluding a relevant variable or underspecifying the model. And why this is a problem? Because if we do not include a relevant variable, it will by the error term, and it will cause some correlation between the error term and the explanatory variable, and our OLS estimators at the end will be biased. So it can occur in two ways. One is due to correlation, one is due to confounding, and this means that if the variable that we did not include in our model is correlated with both the dependent and the included independent variables, our estimated coefficients for the included variables will be biased, and the estimated coefficient will incorporate the combined effects of the included variables and the omitted variable, thus leading to an incorrect interpretation of the relationship between those variables. And secondly, if the omitted variable is a confounding variable, meaning it affects both the dependent variable and the independent variables, the estimated coefficient for the included variable will be biased again. And another problem, which I did not include in the slide here, is the endogeneity, which can occur to simultaneity or reverse causality. For example, let's say that we try to explain economic growth and the relationship between economic growth and investments. Here there is this simultaneity because as economic growth, the investments might increase and are like increasing or decreasing at the same time, and this causes endogeneity. In the reverse causality, there might be so let's say that this is from research I'm working on. So let's say that we are taking a look at the effect of social housing on the vote share of the incumbent party. So we do not know here reverse causality here because as the social housing projects increase, people living there might be more willing to vote for the incumbent party. But when we think of the reverse, maybe the incumbent party choose the places that they will provide social housing according to the their past votes. So they might specifically target the regions that already vote for them. So there is this endogeneity, and this is a result of actually the violation of exogeneity assumption. And how do we solve this? We might add fixed effects. So fixed effect regression is one that is as a solution. Differences design or RBD is another solution to solve this endogeneity problem and the violation of the exogeneity assumption, which Serkan Tucan will talk about after this presentation. So in order to give some background about it, I included what is the panel data and what is fixed effects. So panel data, also known as the longitudinal or repeated measures data, consists of observation multiple entities such as individuals, firms, countries over time. And in panel data analysis, we use fixed effects to refer to a type of estimation technique that accounts for individual specific or time invariant heterogeneity in the data. And these individual specific effects are called fixed or entity specific effects, can capture the unobserved factors that are unique to each entity. So by this, we try to make sure that the error term does not include those unobserved factors and cause a bias in our estimates. So fixed effects allow us to estimate the relationship between the independent variable and the dependent variable while accounting for these individual specific effects. How do we include those? We introduce fixed effects by including individual specific dummy variables, and these dummy variables take a value of 1. So if the individual belongs to a specific entity, and 0 otherwise. And the coefficient associated with each variable captures the average effect of that specific entity on the dependent variable after controlling for other independent variables when we introduce fixed effects. So as a last note, I included some suggestions for how to report those regression results. And this is actually from Wooldridge 2019, Wooldridge 2000 on econometrics. So of course, we should report OLS coefficients because we will be interpreting those estimated coefficients, but it is not always to have the coefficient there and said that it's statistically significant, but we should consider the substantive significance too. And in order to comment on that, to know the units of measurement and distribution of our dependent and independent variables. So a 1% change might not be statistically significant in a model, but it is substantively significant in real life context, considering our data, or vice versa. There might be a 20% change, so according to our coefficients, but this might not mean much consideration of our dependent or independent variables. So it's always a good thing to comment on the substantive significance too. And standard errors should be reported. They are generally reported at the bottom of our coefficients in parentheses, and this makes it easier to compute confidence intervals, so we report them. And R-squared adjust square from the regression should always be included because this is a measure, this is the most common measure for the goodness of fit. And it makes calculation of S statistics for exclude restrictions simple. And of course, we should report the number of observations, otherwise we will not, all of these would not make any sense. So we include the number of observations at the end of our regression table. And this concludes my presentation here. I hope this was helpful. If you want, we can have a 10-minute break and then continue with the R, how to employ, how to estimate OLS in using R, or I can continue.
Thank you so much, Berfin. So I think we're going to get a 10-minute break and then come back. Thank you so much for doing this. If you can't, no big problem, but if you can have a look at your Wi-Fi, you get cut off at some point. If you can fix the Wi-Fi, that would be very, very great. So thank you.
I'm sorry, I will try to solve this issue.
Yeah.
Okay, John. Let me share my screen. Hi everyone again. So I already created the code, but we will go over them one by one. For the first part, we will not be using the data set I share with you, but for the second part, we will use. I always start by setting a working directory, so you may also want to do that. And then now I will create a fake data set. So this is this shows the number of hours that students studied, and this is the score of their exams. I can wait for you to copy that. So there should be 15 observations. So I'm creating a data frame and call it to df. As you can see, there are 15 observations and there are 2 variables in this data set. You can also see the first 6 rows of the data set by the head function here. In the console, you can see the first 6 observations. I will load the ggplot library because we will be using this for visualization. If you do not have ggplot, you might install with install packages command, or you can do that by here from tools and install packages. Then, in order to show the linearity between the dependent and the independent variable, I will create a ggplot, a scatter plot using ggplot. Here, in this case, I will use hours of study as independent variable and exam score as the independent variable. I'm running this. So take a look at this graph. So I know that it's a bit, so we have very little observations. I know, I'm aware of that, but you might sense the linearity in this relationship, I believe. Until that point is everything works for the codes. Okay, so first we check the first OLS assumption that the relationship is linear between those. And then I will try to capture the outliers. In order to do that, I will create a box plot, again using ggplot. And by this command, it will show us whether there is any outliers in our data. If there were any outliers, it will appear here or here as points. But apparently, in our data set, we do not have such a problem, so we don't have any outliers. Now, I will fit the model. This would be a simple linear regression model with only one independent variable. Something.
Just a moment. Can you make your text size bigger? Because the screen is not very big here. So if you can just make your text size a little bigger.
How to do that?
The graph size. Graph size.
Is it okay?
And the graph size, the plots.
And when I okay, I will reshare my screen because you cannot see when I open the. Okay, let's say share. Now, when I zoom in the plots, you should have see the plot. But now you can see the
Yes.
bigger. Yeah. Okay.
Yes, thank you.
Okay. Should I wait for you to copy the codes a bit?
So, do you expect them to write the code, or did you
They
send?
can. I will send them. I will send the codes, but if they want to practice with me, like they
Then
can.
you have to go much slower.
Okay. Sorry.
I mean, we were just like watching. Because we thought you were going to send this to us, because if you want us to code, just let us know. But be
Okay.
very.
Maybe we can go over this one and then with the other data set we can
Okay,
code
fine.
together.
Sure.
Okay, so after seeing the box plots, now I will fit the simple linear regression model with just one independent variable. First, I wrote the dependent variable and then the independent variable, and we specify our data here, and I'm fitting this. And to see to view the model, we use summary function, and it appears in the console. So let's take a look at those. So as you can see, there is this coefficient. We have the standard errors here, our t-value. This star shows whether our estimate is significant or not. We have r squared, so an adjusted r square here. Is there anyone who wants to interpret these results? So how do we interpret them? We want to be a volunteer to do so.
So I think right now they're still trying to catch up with the code.
Okay.
They're a little bit behind. So go ahead and you interpret it. Once they catch up with the rest of the code, they will start helping you.
Okay. Let's start with adjusted r square. As I told in the presentation, we generally multiply it by 100, and then we interpret those. So this means that our model explains 81% of the variation in the data, and this is our coefficient for our independent variable, hours, and in that we can write the, for example, we can write the code like ry, so r beta 0, our intercept is this, let me copy and paste it, plus this is our beta 1, and ours, of course, here in this case of x, let's say, plus error. So this is our regression model. We can write this by looking at the summary. And for any x value, we can predict what would be the y. So we can predict, for example, if a student study for 2 hours, they will get such and such point following this formula, and but this will not be a exact score that they will get. This will be just a prediction of y. So this will be kind of the average of students who studied 2 hours for the exam. So be aware of that. And since the coefficient is positive, we can say that as the number of hours studied for the exam increases, the score they will get will also increase. So there is a positive correlation between them. Let's create a scatter plot with the actual data points. And add a regression line. This should be true. And then display the plot. As you can see, this pink line, maybe I should change that to something more visible. So this purple line is our regression line, and here we see our data points as in the example. And the difference between the point on the regression line and our actual data point gives us the error. And this shady area that you see is the confidence intervals. So how do we include those in our graph? We add this CE equals true. So if I wrote false here, it will disappear, the confidence intervals. Oh, no, it didn't. Okay, it should, I don't know why it is like that right now. Anyways, so I'm moving. Now I will create residual plots to check the assumptions of homoscedasticity and normality of errors. In order to do that, I will create a residual variable from our model. Then I will plot it with an AB line. And it is something like that. So as you can see here, errors are, so the variance is kind of constant. I believe this does not create such problem, and it is distributed kind of evenly. So in the upper part of the line and the lower side. So I guess there's no problem with homoscedasticity with this one. And in order to normality, I will create a QQ plot for residuals, again using the same variable called residuals. And this shows that it follows more or less a normal distribution. And there isn't a problem with that one too. Yes, so this was about the first example. And for the second one, you will need to install and load the Heaven package. And also, you will need the data I send it to you. So we can go over this one by one. Now, in order to read data DTA files, you use read DTA command, and it's in the Heaven library. So I'm defining that. And remember, we use head to see the first few observations in the data. If we specify a number here, we can choose the number of, we can choose the n. So we can take a look at our data. This is a data set that has the average. Actually, it has this variable BWAGHT. This is the birth weight of babies. These are individuals, as you can see, and so these are all babies. This is their birth weight. This is the education level of their father, education level of their mother, years of education, I believe, completed. Their gender, race, I guess, And our main interest is here that whether mothers who use cigarettes during their pregnancies, like usage of cigarettes has any effect on the birth weight. So this is whether they use, whether they smoke during the pregnancy or not, this variable. This is different operationalizations of the birth weight. I guess this is a logged one, and this is in LBS. This is a packs of cigarettes, the number of cigarette packages they consumed. As you may guess, packs and cigarettes will be perfectly correlated. This is the number of cigarettes, by the way. This is not a dummy variable, sorry. This is the cigarette price in their state, and this is the tax rate in that state. So we don't need all of these variables. So I'm creating a sub data set only with some specific variables. I will just get birth weight, number of cigarettes, number of packs, cigarette tax, cigarette price, and mother's education. After doing that, I will again take a look at the data. As you can see, in the new data, we have only 6 variables. Now, I will create again a scatter plot, but I will do this with only one independent variable. The main variable of interest is the number of cigarettes, so I will create with a scatter plot using cigarettes and birth weight. Yes, so did you catch up with me until this point? So did you create a plot?
Who couldn't catch up?
Okay.
Let's did. You just say no, it's okay not to, because this is a training thing, so it's okay to, everyone is perfect. Okay, but I think we have
Okay.
you just continue.
Okay, so this is a bit different from the previous one, as you may see. This is, there are some points that we have a lot of observations, and there are some other points that we have few observations. When you take a look at this, it seems like there is no relationship between those, but it's again seems linear. So I'll continue with others. And I will take a look at the outliers again, using ggplot and using boxplot. Here we see that we have some outliers in our data set. Should we exclude those outliers from our analysis?
Are you asking a question to the class?
Yeah, I am asking.
Okay. So who wants to answer? Speak to the microphone in a very loud voice. Yes.
Can you hear me?
Yes, it's great.
Actually, it seems that we can extract these observations from the data set, but it depends on the effect of that observation specifically on the models. So that's why, first of all, I think we should check whether it has a significant effect on the predicted value. say.
To be honest, I'm never sure whether how to proceed with this in any context actually. So I will also ask this to Serkan hocam. Hocam, should we exclude those?
Sorry, I have no idea what you're talking about right now, but
Yeah, these are the outliers in our data set.
so the outliers. So yeah, the impact of outliers, since this is like a fitted line, let's say there's a one extreme outlier, and that fitted line is gonna be pretty much affected by one outlier, even if there's like so there is so let's say I don't know this is let's say your actually there was one example that I was using in class. So so you're trying to predict votes, for instance, and then there is this particular county in Florida that I was showing you as an example, and that particular country was like super off. It was like in terms of so in terms of prediction, the error was like it was clearly off, like compared to others. And the reason why, when you look at that country, for instance, it was because it was specifically it was using completely different ballot design, and it was a clear outlier. And when you just remove that, the slope was changing tremendously. So sometimes, yes, outliers is gonna like they're gonna affect the slope of the final a lot. But I think that depends. I think it's first you need to just plot things and see whether they are like. It's because sometimes it's just error. There's an error in the data generating process. So yes, that in that case, yes.
Thank you. It was very good explanation for me too. So now that we see that outliers and have that discussion, I will show you how to create scatter plots for every possible pair of variables. So this pairs command do that. I guess this is in, you don't need any library for that. Yes, so this is a bit. So these are the relationships between variables. So this is, for example, weight and cigarettes, weight and packs. So you can see every possible relationship by using this pairs command. So by that we included all independent variables, and we can inspect all relationships here. As you will see, there is this linear relationship between cigarette price and cigarette tax, and it seems like they're perfectly correlated. Again, with the cigarette, the number of cigarettes and packs is perfectly correlated. Yeah, so, and we said that there shouldn't be any correlation between independent, perfect correlation between independent variables. So including them in the same model would bias our results. And there is another way to do these plots, which is using the G-GALLY library. You can first install if you haven't done so, and then use the library. And with this, you can just write this code and what happened? It was working last night, and okay. Oh. it creates more or less the same things, as you can see. So you can, it's better looking like with these, and you can work with the colors and the other properties of these graphs, but it's looking better than the other one. So you can use this library too to generate the pair of plots. And now I will run the multivariate regression. So here there are all these variables we had in the data set. However, I will delete the ones that are perfectly correlated. So I deleted the X, and I will delete the price. Then I will run the regression. Okay, so this is our model. If you did catch up, can someone interpret these results? I just know Alper, so I have to pinpoint him to interpret the results.
That's really our guy, but okay. Here, I suppose each smoked cigarette before or during pregnancy, the count variable cigarettes or packs. Or anyway, whatever the number is here, maybe out of 20, so it's a cigarette packs count. Each of them decrease the birth weight 0.4.
Yeah.
Which is quite significant at the probability of observing this result by chance is 1 out of 1,000. So
And
very, very significant. So you don't observe this by chance. The other one, the tax is not significant, so tax will affect the birth weight. And what we have, mother education. Also, this wasn't effective on the birth weight. So only in this model, smoked cigarette affected the baby's weight.
how, yeah. Is there a question?
Was it correct or no?
Yes, so, but if you also take a look at the adjusted R-square, it's quite low. So it only our model only explains the 2% of the variation in the data set. So this is actually not a very good fit to our data, let's say. I will create a scatter plot again with confidence intervals and the fitted line. Okay, yeah. So our confidence intervals are narrow at the points that we have more observations, as you might see. And when we have less observations, they are getting wider and wider. And the line signals a negative relationship, but does it really a substantial effect? We should take a look at some other factors to comment on that, I believe. So yeah, this is the fitted line here.
By the way, I think we can also talk about first impact of outliers here. Let's assume we have one outlier, so I cannot see the scale. Is it 20 y-axis? Is it not? 200. Let's say you have one where y is 500, let's say. Then the slope is, it's gonna impact the slope of the fitted line. So it would have something more like, you know, it would just tilt, right? The fitted line, if let's say we have one even have a single observation with like the value of 500 as the outcome.
Do you mean that if we not include the zeros, like if we delete the zeros in the data?
I mean, that depends on what you're doing, right? So I'm not sure what 0 is here, so I'm not saying it right now.
Yeah, it might be affecting the results.
I mean,
So
if it's because of measurement error, then yes, we can.
Perfect. May I ask a theoretical question? You hear me?
yes, of course.
Is this the graph was better? Is this a good way of collecting data? Because since you asked question how many cigarettes you smoke, and this animal saying I smoke 17 cigarettes per day.
Mhm.
You see like it's around 0, half a package, full package, 1.5 package. Is that a good way of doing things? Or maybe it's better to use different scale.
Yeah, I think people they're gonna round up, right?
Yeah.
20, 5, 10.
Yeah, this is the problem with survey data, I believe. So you'll never get the exact like you never get the true cigarettes they smoke. They can even lie because they're ashamed of smoking cigarettes during pregnancy or so. So this is, I guess, the problem with survey data.
I mean, there are designs like list experiments, like let's say you are asking a sensitive question, such as, I don't know, like, are you bribing public officials? And if you ask this question, they will say, no, of course I don't, but we know people bribe, right? So list experiment is one like technique that we can talk maybe after this session. So there are techniques. I mean, in this case, it's not you wouldn't use a list experiment, but to uncover sensitive items, list experiment has been one of the main tools used by social scientists. That we can briefly discuss.
I just wanted to add something. Outliers are always not like about the prediction value. So let's say in this data set we see the number of cigarettes. So how many data points we have? Around 50. So we have one data point, I mean number of cigarettes 50 and one y value for that. So now we are fitting a line on the whole thing. So that one item, in that index will affect that, let's say almost 80% of the data. So what I'm trying to say is maybe in the data sets into some some ratio in the terms of number of cigarettes, and then fitting different models for those ranges would make more sense. I mean, it can predict the values much better. That's nothing about that.
Okay, is it a question to Serkan Hocam or me?
This already was like question.
So just a comment.
So you're like fitting.
I said that. So let's say you have one data point in 50, right?
Oh, that's that. Okay,
Yeah.
sorry.
So that's 50, and we have only one data point there. So we are fitting a whole model on that.
Yeah.
That one will affect the whole data.
Yeah, that was kind of my point. Sorry, I thought that was so yes, right. That little one point is gonna just move that fitted line towards 0, right? So and that's the problem with OLS, like so the impact of outliers. So if you just remove that single one point, it's gonna be more flat for sure, right? So yeah, that's right. So that's why I think it's important to show. I mean, and if you read research papers, you'll see that, right? So sometimes you'll see a sample where you remove outliers and the results hold. So that's a nice thing. So it shows that the results are not model dependent. In this case, model.
Can I ask a question about outliers? So we're talking about point that success, but if we take this as an outlier, we have to take not we have to take, but we can take 40 also 45 as outlier. So I wonder, according to what can we put the correct threshold?
Well,
For example, maybe 90% of the data, can we say?
I think that depends on what kind of data you have. For instance, like you can, I don't know. I mean, first just look at the scatter, like just I don't know, create some sort of a scatter plot and just visually inspect. And most of the time, if you just like, I don't know, maybe it's just like the top 1 percentile or maybe 0.5 percentile or something, right? There are like these decision rules where people just I don't know, they use maybe I mean I think it depends on what kind of the distribution is important there. So maybe like I don't know, 0.5, 0.1 or something like that. But there's no like a recipe. I mean, it's like there's no like that.
I will move on to the assumptions, and this might also be helpful because now we will check whether the distribution of residuals are approximately normal. For that, I will use a histogram and model the residuals. I get the residuals from that. So this is the distribution of residuals. It seems like normal, like it seems like a normal distribution. There is not much problem with this distribution. Then we can also create Q and Q plot as in the first example, which will be the same as inspecting the histogram. So for checking the heteroscedasticity, I will plot the residuals with an AB line. And yes, so here I guess there is an issue of heteroscedasticity because the variance is not constant, and that our estimates could be biased. And how to solve this? We need to have a theory, and we need to understand our data better to create our model. This was just to show you that you can how you can inspect for heteroscedasticity and other OLS assumptions using R. Yes, so that was all from me, actually. I hope this was helpful. And if you have any questions, I might try to answer, but I'm not sure whether I will be able to. But I can try.
But can you also send this R file to me so that I can share it with other people?
Yes, I will send the R file and the slides to you.
Thank you so much. In case people couldn't follow, do you have any questions?
Just a small theoretical question about the plot for a regression line. Could you please use plot where you solve our
The plot too,
yes,
this
that's
one. Yeah.
That's a theoretical question. Just seeing this plot, is it okay to accept that I apply the regression model to this data set? I just want to learn the statistical.
This is the regression line. This is a fitted line created by estimating a model. So yes, you did estimation here, but
If I check the distribution of the data,
mhm.
it seems like not normal distribution. But I am not sure.
What do you
I
mean
don't-
by normal?
You know, the assumption of the regression, there are three different assumptions of the regression. Actually, with linear models it has assumptions. So one of them is normal distribution of the observation in the data set.
No, it's fine.
No, it is normal distribution of the errors.
Yeah, the only assumption is about the error component, not the variables themselves. So I mean, yeah, it's like, it looks weird in the sense that there are like all these people, because of round numbers, right? They just round them up. And yes, so it is, I mean, there is the saying, right? All statistical models are wrong, but some of them are useful. So here, it shows the pattern, right? Because there are lots of zero, like there are lots of people at 0. Then there are fewer at 10, 20, if I see correctly. And as you see, if you just take the means of those, the weighted mean, so it tends to decline, and that fitted line shows that trend. So yes, is this perfect? No, but no statistical model is perfect at all, right?
I understand the point.
Lastly, I might show you this website. So if you wanna like play with the data and get the ideas of OLS, you can choose a data set from here. You can fit a regression line. You can inspect the regression table. So this is a website like you can shuffle values, etc. I might also send the link in the email.
Yes,
And
please.
yeah,
Yes,
you can.
please. This is very useful for me to teach as well. I didn't know this. It's very good.
There is also a Shiny app as well for OLS. Just Google Shiny app. This is not Shiny, right? No, it's not.
No, this is not Shiny.
Yeah, let me see.
Yeah.
Just Google Shiny app OLS. You'll also find another one.
Okay, thank you for having me and listening my presentation. I hope this would help you in understanding difference in differences and RDD. From the point I learned DID, I cannot think of anything else. So I wish you a great afternoon because it will be so much fun, I believe. Yeah, okay.
Great. Thank you so much. Let's
Thank you.
Okay, so right now, I think we're going to lunch. After lunch, we are going to continue with Serkan Hoca's session. So thank you so much. We're all going to lunch. Alberto, thank you so much. Take care.
Thank you, Bad.
Thank you too. See you.
By the way, before we leave the room, I have some